I turn it over to you, Ryan.
Awesome. Okay. Well, yes, again, thanks for inviting me here. And it has been a while since I've been at Goddard. I did my graduate school there. I definitely have very fond memories of Building 34. But today I'll be talking with you about uh, essentially a world that I've been interested in ever since grad school, which is Titan, and treating it as treating exoplanets as Titan-like worlds, especially in the era of the Habitable Worlds Observatory, which we hopefully will be in after James Webb and Roman. Let's see if I can. There we go. Okay, so the first question, why Titan? What is so compelling about this world? Why study it? And one of the first things, big takeaways is, well, when you look at it here in two different parts of the spectrum, one of them is completely, the surface is completely opaque, which is on the left and the visible, and then in the UV, you actually can see down to the surface. So that tells us in a way that this is a world with massive aerosol hydrocarbon hazes completely covering the surface from us in the visible. And so why, when I think about why Titan, I think about really what interests me. And one is right here in our solar system. It's for us to explore. We've already been there once with actually to the surface with the Huygens probe. And we'll be going back again in hopefully the late 30s with Dragonfly. And so it's where we can actually go. We could even put humans there potentially. It's not so far away that we would need some kind of exotic form of travel, like faster than light or anything like that. We could theoretically go there in a reasonable amount of time. And so we can go there, we can actually get in situ measurements, either robotic or potentially one day with humans. And that thick hydrocarbon haze that I mentioned, which is again visible in the there in the visible in the top left, really leads to ultimately a hydrological cycle similar to the one on Earth, just with it being so cold on Titan, instead of water condensing, we actually have methane and other hydrocarbons condensing. So we have this world where lakes are forming that does look like they are evaporating at different over different ages. And so you have liquid on the surface, and then with this aerosol formation with these various hydrocarbons, you get organic material falling down to the surface that could be some kind of beginning piece to as a catalyst to life forming. And then with it being a rocky world that is very exotic compared to Earth, it's also a fun world to study for when we think about other worlds out there outside of our solar system. This is something that I always like, is to take Titan, put it around other star types and see what happens. And again, just to get you, I mean, I think by now everyone should be fairly familiar with Titan. But just some of the basic statistics here compared to Earth, just to get you a little familiar, guide. And give me 1 second. I'm just gonna close Teams so nothing pops up. Okay. So here's some of the basic numbers for Earth and Titan. And then I mentioned Dragonfly. And so just point out again that the plan is to go to Titan. And I believe the arrival time is now in the late 30s. There was a recent delay by about a year. I think that's the second or third delay. But it's just a massive dual quadcopter mission to Titan, where we'll actually be able to fly from site to site. and study the surface and the atmosphere as it moves from one location to another, essentially as it hops, as it hops from one spot to another. And so unlike Huygens, where we only just got that one profile as it plummeted through the atmosphere, Dragonfly will be able to get us a whole slew of surface and atmosphere composition information measurements as it moves from site to site. So that's a little bit about why Titan, and why it may be interesting. But we also had in the Astro 2020 Decadal Survey, ultimately a recommendation for a 6-meter inscribed diameter infrared optical ultraviolet space telescope, which is really essentially a mix between the LUVOIR B platform, which is about an 8-meter dish, and HABEX, which is now what we're referring to as the Habitable Worlds Observatory. And I'm sure many of us here in the talk have gotten the emails and have been part of the various start and following the GoMap progress. So this is all very much in its infancy, but the Habitable Worlds Observatory project is moving forward. Now, first off, are there any Titan-like exoplanets out there? We have, of course, Titan, but what about other worlds outside of our solar system? And there's the potential. It's still a candidate exoplanet. It's definitely not confirmed around Barnard star, which is referred to as Barnard star B. And it's actually kind of funny. It has a fairly storied and dramatic past. Back in '63, Peter Van de Kamp said that he discovered astrometric he had astrometric results showing that if there was a Barnard star planet, it was no larger than a Jupiter mass planet. And so that kind of essentially would put a limit on what may be there. But then a couple years later, George Gatewood came along and said, actually, no, I can't. He could not recreate Van de Kamp's results, and that it was actually discovered that the astrometric results were due to a discrepancy with the telescope Van de Kamp was using. So then it put everything about a potential Barnard star planet in doubt, and many years actually passed, 26 years really, with nothing exciting. And then in the era of Hubble, with the era of Hubble, Benedict et al. Came along in '99 and showed that if there were any planets around Barnard star, they could not be larger than a Jupiter-sized planet. So kind of getting back to what Van de Kamp had been working on. And then through the early 2000s into the 2010s, really just null result after null result. And then now I thought this seemed more recent, but it's been actually about 5 years now. In 2018, Ignatius Ribas came out with a group showing that from various ground facility, especially with the HARPS ground facilities, and a whole slew of radial velocity data, they actually saw evidence for a super Earth, a Barnard star B, with a minimum mass of about 3 Earth masses. So it's like, wow, okay. So this seemed like a pretty big deal. It was still considered a potential candidate, just a potential because it was radial velocity, not transit. But unfortunately, then, as I said, this is a very storied, very dramatic and storied past with Barnard star. A couple years later, Lubin et al. Came out and said, actually, no, it looks like this is due to stellar activity as a proposed culprit for the planet signal. So we're kind of back to square one. Though, if we actually just though I realized I did the math, if we were going at the speed of Voyager 1, as it's going right now, if we headed towards Barnard star, we would get there in the year 1005, 959, and be able to essentially say whether or not there's actually a planet there. But hopefully we'll figure out before then. But either way, whether there is a Barnard star B or not, this Ignatius's 2018 paper was still very exciting because this was a potential world that was at the snow line for its system. So it gave us the idea. It was like, okay, well, maybe we can have some other Titan-like worlds out there, because one of the characteristics that we think of, at least when I say Titan-like, is that this is a rocky planet, rocky world near the snow line for its host star. Other Titan-like features I've listed here, of course, hazy atmosphere. I mean, that's one of the most ubiquitous characteristics that of Titan, and then the methane precipitation, and very reducing, which simply means just very low oxygen. So here's some of the other, and like I said, this is approximately 3 Earth mass planet with about 233-day orbit. But again, whether or not Barnard star B is truly present, we can still model worlds around other star types with kind of Barnard star B in mind. And so how might we tackle this? Well, first off, we could turn to essentially my bread and butter, which is photochemical modeling. So in this work, the first step I use is the 1D photochemistry model, referred to as ATMOS. And this diagram is just a cartoon illustration of how the model works. You have lower and upper boundary conditions into the bottom and top of the atmosphere. And then you have hundreds of reactions occurring at each layer, while diffusion is allowing the gases to move throughout the layers. This reaction network I use is based on the initial one. I'll refer to this as Titan 2.0, and you'll see why a little later. This one is based on the work of Eric Hubbard from a Titan network he developed back in 2012. It has over 700 chemical reactions, 91 species, and fractal haze. So I can go in there, with this photochemical model, I can create templates of various worlds. And then to actually study what then if I want to actually characterize them, I can turn to the planetary spectrum generator. Again, with this being a Goddard talk, I think a lot of people are probably familiar with PSG. This is Geronimo Villanueva's amazing work, where you can select different types of planets. You can play around with the atmosphere, surface composition. You can adjust the target. And then what's really great is you can select the instrument or the observing telescope that you're going to look at your target with. So Geronimo and I went in to PSG and first wanted to validate, before we got too deep into Titan, Titan-like worlds, we needed to validate it against Titan observations. So we took results from European Southern Observatory, ESO, and Cassini-Huygens, and then compared those data results or those observations to PSG. And so this is the first one of these comparisons where This is you can see in orange, this is Kokoschka 98 and McCord 06 versus PSG. And this is a reflectance spectrum. So essentially, it's just the shininess. This is the I over F versus the wavelength. And then another comparison or validation attempt we did was based off of Ty Robinson's Titan solar occultation work back in 2014. This is essentially just the Titan was between between Cassini and the sun, looking back towards. So Cassini is looking through a Titan's atmosphere, and you get this occultation data. And so our results actually match everything pretty well. There are a few places here and there where things are off. We realized that there's certain gases missing. We didn't have ethane there in the reflectance spectrum for the older observations. We noticed that there's ammonia missing. And then there's some hydrant data. There's some spots where the peaks don't match because of missing hydrant data from, I believe, from hydrant 2016. But overall, these were good matches. So once we comfortable with that, then we needed to turn to a telescope. So initially, so of course there is no HWO yet in PSG, but what we can use is we can start with LUVOIR. So these first results are actually with LUVOIR A, and then I moved down to a more HWO-like telescope as we progress through. So with LUVOIR, we have the most relevant instrument to use is Eclipse. This is the one that allows coronagraphy and direct imaging. And this is one of the first results where with LUVOIR, so this is the 15 meter, this is looking at Barnard star B, or sorry, this is looking at Barnard star with if you just place with Titan. So if you took Titan and just threw it into the Barnard star system, this is what you would get. And you actually see it's amazing. LUVOIR A really was had amazing capabilities. So you can see here, especially in the near IR, these methane these methane windows would be very easy to characterize. The noise bars are extremely low. And then it gets even better if you apply the Barnard star B characteristics. So I had the mass from before from the radial velocity measurement, and then there's a mass radius relation that you can use from Satinol 2007, where you make assumptions about the water content of the world, and then you can get a radius. And so this was one of those radius. This was about 11,000 kilometers, and then this was the surface gravity. And again, you see we have the Rayleigh tail in orange over in the UV, which is very indicative of the presence of a thick haze, and then the methane windows are extremely visible in the near IR.
Ryan, what was the exposure time on these things?
This was less than 200 hours. I don't remember off the top of my head. I have for the later ones, I have hours. I don't remember this one specifically.
Okay, thanks.
Let me write that down, Avi, because I can send that to you. Okay. And then, so this was LUVOIR A. And like I said, we're moving more and more towards something that's HWO-like. And so around this time, I needed to also make upgrades to the model, to the photochemical model that I'm using to produce the essentially to produce the mixing ratios and the chemical profiles that feed into PSG. And so this included an increase in the number of chemical reactions and improved isomer chemistry. Going back to Eric Cabral's work, he came out with an update to his network in 2013, which I've recently taken to incorporate the isomer chemistry. And so isomers, just very easily, this is a species where you have the same amount of atoms in each element, but the arrangements are different. And specifically what I've incorporated are the C3H and the C3H2 isomers. And what's great is really how much more robust this has been able to make the entire network, especially when we look at haze formation. And so example of that is in these 3 reactions on the bottom left, where it shows CH mixing with the 3 different C3H2 isomers and how that destruction leads to C4H2 and hydrogen. Now, I specifically picked these 3 reactions from my massive reaction list to show you, because if you consider very simplified pathways for benzene formation on Titan, C4H2 is along one of the paths. And there's other ones here that I could highlight, but I just wanted to specifically show C4H2. And so by having these isomers, what you get different reactivity. So these 3 reactions will not all, their rate coefficients will not all be the same. And so you really open up the ability for C4H2 to build up, which then ultimately leads to improved pathways for C6H6 or benzene. And benzene is essentially is one of the steps in haze formation on Titan. And within the photochemical model, we can go in, I can pick a species and pick a specific reaction, have it turned into whatever type of aerosol haze I would like. And then here's our example showing the difference from the pre-isomer model to the post-isomer model. So I just refer to these as Titan 2.0 and Titan 3.0, where Titan 2.0 is before these isomer upgrades. And the plot here is showing benzene's mixing ratio on Titan, on Titan from before and after. And so you can see there's a noticeable difference between these two, especially near the surface. But just overall, benzene's mixing ratio, benzene's abundance is higher. And another way that we can connect this to the haze formation is by considering the optical depth. So the optical depth is really just indicative of how thick the atmosphere is. And you can see here that for the absorption optical depth, when it was pre-isomers, it was optical depth of about 11, and it almost doubled moving to the 3.0. Now I want to start stepping back a little into the newer templates I'm working on now with this upgraded isomer network. So, and moving back to Barnard, so moving back to this Titan, potential Titan-like world. And so the Barnard stir B that I'm working on is one that actually has a estimated altitude height of about 130 kilometers. This is just based on doing scale height approximations and you can work this out from the scale height. And so what I've been doing now for the past months or so are moving, essentially gradually converging the model down towards that end goal of 130 kilometers. And it's not there yet. So what I'm presenting today are the preliminary results, where we're currently have gone from 1400 kilometer atmosphere to 720. And essentially I'll just keep doing the model runs and we'll get it further down. But I have here the star types on the left, along with absorption optical depths, again, to show you what's happening with the haze. And what I've run so far are 3 different types of M stars, G star, which is just our exact the data directly for our sun, and a K star example. And I just will point out the one of the M dwarfs is actually modeled after TRAPPIST-1 from, it's an average of Peacock et al. Data. And then for the surface mixing ratios, well, I have multiple surface mixing ratios, but what I want to point out are the methane and CO2 values, and just highlight that these are actually held fixed. So across all of these star types, and for this parameter space here, I have these held fixed, and these are based on Titan surface mixing ratios for methane and CO2. And then again, here's the other planetary parameters: the surface pressure, the surface temperature. The surface temperature is kept at Titan. The surface pressure is a little less than 4 times higher. And then we're using this much larger planet radius. And the gravity, again, this is another goal. The gravity right now is set to 2.4. Titan is about 1. I believe it's about 1.25. And the end goal is to get it back to 10.4. And so now let's go back to the spectra. So I wanted to first, I realized people would probably think, okay, well, like, James Webb is up there. What about James Webb? And so I did want to do a quick run for James Webb and see if you could even see this Barnard star B. Because if you could see this puffy Barnard star B, or if you couldn't see it, then there wouldn't even be any reason to consider Titan. And unfortunately, you can't. After 200 hours of exposure time, you can see here the error bars here, and for both NearSpec Prism and MIRI. I picked these because these are instruments I'd used in previous projects when working with James Webb, and it's just not going to work. The error bars are still way too large to be able to pick out any kind of features. So now let's actually try something habitable worlds like. And so what I've done is taken the LUVOIR B platform, set it to 6 meters, and then go through all of the band passes while adjusting the resolving power for each of them, and setting, I'm still doing 200 hours. So this is, and actually I didn't present the results here today, but I actually did try cutting it in half down to 100 hours, and you could still see these features. It's just 200 was just what I had ready to present. So this is for the M8V star. And again, this is the puffy Barnard star. So puffy just meaning that it still has a very extended atmosphere, but it's a large world. much larger than Earth or Titan. And right there in the near IR, we have methane windows and we have noise that, and we have the simulated error bars on the data points that would definitely make this characterizable.
I think we lost you, Ryan. I see you're unmuted, but I can't hear you right now.
Hey, Joe,
Oh,
can
wait.
you still hear me?
Yep, I can hear you now.
Okay. Okay, I think it cut out. Okay, sorry about that. Okay, so as I was saying, this is still characterizable with in the near IR, and really you can see the only regions are out towards the edges of the near IR, and then the UV is where it just grew. The noise is the error on the data is so large, you're not going to be able to pick anything out. But for something like getting a characterization, at least with the methane and potentially other gases that could be in these regions, this isn't that bad. And then this is the GJ876 version. And then the TRAPPIST-1. Now, there may be something, if you're really used to staring at spectra, especially hazy worlds, so you may notice something here that the Rayleigh tail seems to be absent in these results. Jade Chiclair in 2016 showed that if you shows that in this figure on the right, shows that as you increase haze from essentially no haze in the top left to 2 times the haze in the bottom right, you get this this dip in the UV, this Rayleigh tail, start to form as it moves from 0.2 to 0.6 microns. And this is something that would potentially be detectable. It would be essentially a beautiful hallmark of a hazy world outside of whether or not we can see the methane windows, because you can have methane, you may not necessarily have haze. And if anything was interesting, her work showed that as you increase the haze, you can also potentially decrease the depth of those windows. So it's almost even possible that you could start to lose some of the methane features, even though there's methane there, but still see this very clear Rayleigh tail in the UV. Now, my puffy Barnard star B results don't show that. And unfortunately, I don't know why yet. I highlighted here the, again, the absorption optical depths. And the absorption optical depths for the different star types. And I also went back, I don't have it here, but I went and looked at when I've run the same new network with Titan around different star types. And it looks like you get about a double in the optical depth, where for the G star, it would have been about, or actually, no, I think it's actually about 10. Sorry. For G star, I think it's for Titan, it ends up being an optical depth somewhere around 1 to 2 or so. And then with this new network, it ends up being about 10 or so. So it looks like it may just be that even though I was producing haze in these bolded runs, it might be that it was just low enough that it's not appearing it's not affecting the Rayleigh tail yet. And this is actually something, one of the next things I want to start to play around with is adjusting the methane and CO2 ratios to change the is another way to start changing the methane, changing the haze amounts. So the next steps, as I've pointed out, are to continue modeling down to 130 kilometers. And along with adjusting the methane CO2 ratios to see how it impacts the haze, I also want to be able to run through various methane amounts that would range from abiotic to biotic surface fluxes. And then, as I point out, there's something strange going on with the Rayleigh tails that I want to understand. I'm assuming it's going to follow Jade's work, and it's just a matter of being right below a point. There's probably almost like I'm expecting there to be like a step function where once I have a specific amount of haze, it will start to turn over and all of a sudden the Rayleigh tail will reappear. But really what I'd like you guys to be able to take away from this is what we see here in these in these plots in white, where if you have a 6-meter telescope, which would be indicative of the Habitable Observatory, we can characterize with this, and we can do this at least all the way down to 100 hours of exposure time, which is not something too extreme. And this is, again, this is preliminary work. It's possible that this could go even, that I could pull that exposure time down even lower. And so that's the end of my talk. And are there any questions?
Awesome, Ryan. Thank you so much for the great talk. Awesome work that you're doing. So yeah, we have plenty of time for questions. So if anyone would like to ask Ryan anything, please feel free to raise your hand, or you can post them in chat and I can read them off. While we're waiting for that, Ryan, I'll kick off the first one here. So not to potentially ruin the conclusions here, but you're talking about moving your model, moving it towards a lower atmosphere, moving it towards the 10 meters per second surface gravity. Are you seeing that's, as you start shifting towards that, is that hurting the detectability of these features, or is that?
No, not exactly. No, really, it does not, from what I can tell. No.
Okay.
The only thing it hurts is the ability of the model of the photochemical model to converge, because I'm essentially kind of scraping off parts of the pressure space at the top of the atmosphere and then asking the model to converge to this new pressure, this new top of the atmosphere pressure. And it doesn't really like that. But no, as far as what I can tell with spectra, I'm not seeing anything now.
Awesome.
Avi,
That's
I
great
see
to
your
hear.
hands raised.
Yeah, Avi, go ahead.
Hey, yeah, great talk, Ryan. I was wondering about the question of orbital distance for a Titan-like world around an M-Dwarf. What did you use for the orbital distance? Did you kind of base it on the stellar insolation expected?
Yeah, so I based it on it was based on Barnard star B, which is about 0.4. And then so if I don't use Barnard star B, then I base it on Titan's, the amount of flux that Titan's receiving. And then that I can just, the models will update when you move it to different star types. It will just account for the flux to keep it at that same amount. So whatever flux Titan is receiving now at about 0.1 AU, if I change the star type, it will keep it, so it will give it that same flux.
Gotcha. Okay.
And I can change, and again, like I said, I can change that for whatever. It doesn't have to be exactly Titan's incoming flux.
Yeah. Yeah. No, it sounds good. But then I guess I was wondering about the inner working angle that you were assuming for the chronograph. Because
So
obviously it's super different or it could impact M stars compared to
So as far as I can tell, when I ran, so with PSG, when I set everything up in there with the distance, from what I could tell in the geometry section, it was still showing, it was not showing, I was not seeing any inner working angle issues.
okay. Interesting. All the way down to the UV or out to the IR, I guess.
Yeah. And
Interesting.
I can, and I'll write this down too. What I can do is, I can send you, I can probably like send you some screenshots from the runs or something so you can see how PSG is setting it up.
Yeah, I'm happy to help. For sure. Or take a look.
Great. Anyone else have any other questions for Ryan? I have a one that's or about the Rayleigh tail that you're not quite seeing yet. If you go back to Jade's results, I haven't read this paper, but what is the 2 times Haze referring to? Is this referring to Titan?
I don't think so. But now that I'm,
because you're right, like it really has that hard, like it looks like
right.
0.1 to 0.5, and I'm just
You
like,
know,
what is that 0.1 referring to?
oh, right. You know, I'm not sure, Joe, off the top of my head. I I think I actually have the PDF open like directly behind this probably. But I'm not sure.
Yeah, no worries. Yeah, I was just curious what
yeah.
that was referring to, and yeah, just wondering like how much of an increase of the haze until you start seeing that tail come in. But
I do think it is related to Titan though, because I've looked at the spectra, like the Titan spectra so much, and this that looks like it actually does look just like Titan. The black data, the Neff et al. Data looks exactly like Titan spectra.
gotcha.
But I'll double
Awesome.
check exactly what that is, and I'll tell you. I'll let you know.
Sounds good. Appreciate it. All right. Any other questions? All right. Well, not seeing any. I think we'll end it there. But Ryan, thanks again for the awesome talk, and thanks everyone for coming out to our last Exoplanet seminar of 2023. Again, as a reminder, we have our first one of 2024 in person on January 4th at Greenbelt. Ryan, awesome work that you're doing, and I hope you have a great new year and everyone else on the call does. And I will end the call here. Thanks again.
Awesome. Yeah, thanks everyone for coming.